Welcome to Treasures of Maths. Today we're fooling around with factorials. We start with an old problem, which is this. 100 factorial is defined as 100 times 99 times 98 times 97 all the way down to 2 times 1. This large number will end in a row of zeros. How many zeros? So just let's remember, the exclamation mark is the factorial function. It's usually a button on your calculator, but it won't go up to 100 factorial usually, and even if it did, it wouldn't give the full display of all those numbers. So we've got to have another approach than use the calculator. So reminding ourselves, 1 factorial is 1, 2 factorial is 2 times 1, which is 2. 3 factorial is 3 times 2 times 1, which is 6. 4 factorial is 4 times 6, which is 24. 5 factorial is 120. These numbers are increasing very rapidly indeed. You might even say exponentially in a loose sense. As an aside, 0 factorial is 1 for reasons of logic. Notice that 5 factorial ends in 0. And all the numbers from there onwards will end in at least 1 0. The question is, for 100 factorial, how many? If we continue down to 10 factorial, that will be 3,628,800, ending in 2 zeros. Where are the zeros from? One of them is from the 10 itself, and the other is from the 5 times 2. So here's the insight. Every time a 5 occurs in the product, we will get a 0 on the end. There are always plenty of 2's around from the even numbers. So we need to know how many 5's go into 100 factorial. So we think about it. 5 squared goes into 10 factorial. 1 from the 5, 1 from the 10. 5 cubed goes into 15 factorial. From the 5, the 10, and the 15, that will end in 3 zeros. 5 to the 4 will go into 20 factorial, but when we get to 25 factorial, that will actually have 6 zeros because 1 is donated by 5, 1 of them by 10, 1 of them by 15, 1 of them by 20, but 2 of them by 25, because 25 is 5 times 5. So if we think about the numbers up to 100, all the multiples of 5 will donate a 0 on the end, but the multiples of 25 will donate 2 zeros on the end. So what we have is 24 multiples of 5, add 4 extras, the ones I've underlined, so 100 factorial will divide by 5 to the power of 24. It ends in 24 zeros. If instead of 100 factorial we tried 1,000 factorial, then we'd have the multiples of 5 and 25, but also multiples of 125, and we'd have to take those into account. So there's a question for you to have a go at. If we do 1,000 factorial, how many zeros will that end in? Here's a few more questions about factorials. 100 factorial, we know it ends in 24 zeros, so it's pretty big, but how large? In other words, if I was going to write it in standard form, what would the power of 10 be? So I've tried my calculator, and it'll go up to 69 factorial, which is roughly 1.7 times 10 to the 98. 98 numbers, not all zeros, but it won't go any further. You could try a spreadsheet or a more powerful calculator, which we will try in a moment, but first there's a nice formula or an approximation called Stirling's formula, and this says that n factorial is roughly equal to the square root of 2 pi n times n over e to the power of n. The wiggly sign means approximately, but it also means the approximation gets better the bigger n is. And the e number is the special number e, 2.718281828, etc. So this approximation has two special numbers in it, pi and e. These numbers really get everywhere in maths. If you're wondering how this is proved, it's proved using integration and natural logarithms, if you know about those things. So let's apply Stirling's formula to 100 factorial. 100 factorial will be approximately the square root of 2 pi times 100 times 100 over e to the 100. Now my calculator won't do 100 over e to the 100, but I can take out the 100 to the power of 100. That's 10 to the 200. The square root of 100 is also 10, so I've got 10 201 times, and I have root of 2 pi divided by e to the 100. My calculator will do that, and will give me 9.325 times 10 to the 157. So this number, 100 factorial, is roughly 9 times 10 to the 157 using Stirling's formula. Huge number. How good is this approximation? Well, I went for a spreadsheet and worked out 100 factorial on the spreadsheet, and it gave me 9.333 times 10 to the 157. So the power of 10 was right, but also the number itself was pretty good, and I've worked out that is 0.01% error, which in a number of this size is not bad at all. Factorials. One application of factorials is in permutations and combinations. In other words, an answer to the question of how many ways are there. And n factorial is the number of ways of arranging n unlike objects. So if Postman Pat had 10 letters for 10 houses, the number of ways of delivering these, one letter to each house, is 10 factorial, which is 3,628,800. So if Postman Pat delivers these letters randomly to the 10 houses, the chance of getting it right is 1 in 3,628,800. Better odds than winning the lottery, but actually fairly low. Postman Pat would be better to look at the addresses and deliver them using that method instead of at random. What else about factorials? You might be wondering, what about adding up factorials? What if we add up 1 factorial, 2 factorial, up to 100 factorial? Is there a nice formula for doing this? We can always use a spreadsheet or a calculator, but is there a formula? So we're looking for a formula for sigma r factorial from r is 1 to n. And sadly, there's no nice way of doing it. You've just got to go back to the calculator or the spreadsheet and do it longhand. But there is a nice formula for this related and similar question. If instead we want 1 times 1 factorial, add 2 times 2 factorial, add 3 times 3 factorial, up to 100 times 100 factorial, there's a nice neat way of doing this, which is called the method of differences. Just note how Bidmus applies to factorials. 3 times 3 factorial means 3 times 3 factorial. It doesn't mean 3 3's factorialed. So method of differences. We take the terms. 1 times 1 factorial is 1, which is 2 factorial, take 1 factorial. 2 times 2 factorial is 4, which is 3 factorial, take 2 factorial. 3 times 3 factorial is 3 times 6, 18, which is 24, take 6, which is 18, and so on. And in general, the way this works is 100 times 100 factorial will be 101 take 1 times 100 factorial, multiply out the brackets, 101 times 100 factorial, take 100 factorial, which is 101 factorial, take 100 factorial. So this pattern works all the way down. Add up the right-hand sides, everything cancels, the 2 factorial with the minus 2 factorial, the 3 factorial with the minus 3 factorial, and so on, just leaving, finally, 101 factorial, take 1 factorial. Okay, bonus. Factorials can be extended to non-integers using something called the gamma function. So, for example, we can have a half factorial which equals root pi divided by 2, for example. For integers, it gives you the same as our usual definition, but for non-integers, it is useful sometimes to extend factorials to these numbers as well. And here's a final question for you. We worked out at the start the highest power of 5 that went into 100 factorial. Your final question is, what would the highest power of 2 be that goes into 100 factorial? In other words, if we write 100 factorial in binary, how many zeros will there be on the end? So that is fooling around with factorials. This is Gold Standard Maths, and I'm David Forster.